first of all, this question asks two things. It asks to verify the identity for 30 degrees and then prove the identity. Now, verifying an identity is kind of annoying because you have to still do the left side and the right side, but you plug in the angles. So you would have secant of 30 degrees, 1 plus cos of 30 degrees on the left side. On the right side, you have 1 plus secant of 30 degrees. And the reason verification is a little bit annoying, because once you've proven something, and often proving is easier than verifying, once you've proven something, you've just said it works for all angles. So you wouldn't need to verify ones in particular. But if you do verify, you're going to have to use your unit circle. How do I do this? Well, cos of 30 degrees is, unit circle blanks. Root 3 over 2 or 1/2, cos of 30 degrees. Root 3 over 2. So if cos of 30 degrees is root 3 over 2, then secant of 30 degrees will be 2 over root 3. So we can use our unit circle to put the values in. And just like a proof, you need to use your algebra skills to get both sides to be the same. One of the things that we do with our algebra skills in a proof is we write both sides as a single fraction or simplify as best as we can. Okay? Right here, looking at this one, I could distribute that. Can you see that 2 over root 3 times 1 is 2 over root 3? And 2 over root 3 times root 3 over 2? Can you do that mental math quickly? Can you see that the 2's would simplify, the root 3's would simplify? Are these the same? Yes. Therefore, the left side equals the right side. You have verified. I'm not going to put QED because it wasn't a proof. I'm going to save that QED for the proofs because they're special. Now, to prove it, remember when we prove something, we draw the line, and then we use our skills with changing things, the tools that we have, so you know that secant is 1 over cos. And one of the strategies that you've probably seen already with the activity we were doing yesterday, that if you change things to sine and cos, often you can solve things quickly. Same thing happens here. If I distribute the 1 over cos, I'm going to get 1 over cos theta plus cos theta over cos theta, which is 1. And the powerful thing about the proof is that you have now shown it works for everything. So this means that if you plug in 60 degrees, it would work. If you plug in 45 degrees, it would work. If you plug in 12 degrees, which isn't on your pie plate, and used your calculator, it would work. So proving an identity means that this is true for all angles of theta that are possible. For part B, first of all, it says verify. So again, I'll put my left side and my right side, and it's for 30 degrees. So on my left side, I have 1 minus tan of 30 degrees. On my right side, I have cotangent of 30 degrees minus 1 over cotangent of 30 degrees. Tan of 30 degrees is Do you remember? Root 3 over 3. So if tan of 30 degrees is root 3 over 3, what's cotangent of 30 degrees? The reciprocal. Our job is to get those to be the same. And this is where a lot of working with identities is fraction work. If they're not the same, then a main goal of yours should be to change both sides to a single fraction. How do I change something to a single fraction on the left side? I would need a common denominator. Can you see that the common denominator, I could multiply this by 3 over 3, and then I have a common denominator. So on the left side, my single fraction becomes 3 minus the square root of 3 all over 3. On the right-hand side, I have fractions inside of fractions, divided by fractions. So whenever you have dividing and fractions in your numerator and fractions in your denominator, first get a single fraction in your numerator and a single fraction in your denominator. So right now, can you see that I do not have a single fraction in my numerator? If I wanted to get a common denominator between these two, I could multiply the 1 by root 3 over root 3. Then my top would become a single fraction. What would it become? 3 minus root 3 all over 3. Divided by, slide this down, divided by root 3 over 3. And now that I have a single fraction on the top and a single fraction on the bottom, yeah? Oh, sorry, that's just a mistake. Thank you. Why did it switch? It wasn't supposed to. I like to make the middle line longer and thicker. Yes? Get rid of a square root too? I mean, it must be Friday. So ready to go home. All right. Whew. Now we've corrected both of our mistakes in that line. Yeah. And now we have a single fraction on the top and a single fraction on the bottom. What do we do when you have a fraction divided by a fraction? Multiply by the reciprocal. And I have 3 minus root 3 over root 3 multiplied by the reciprocal root 3 over 3. Something I do before I multiply this out. Notice this one has a minus sign that would get grouped together. Nothing can cancel that one out unless it's exactly the same in your denominator. But can you see that in your other multiplication, we have this one and this one are identical, so you can simplify that. Once that simplifies, what are we left with? 3 minus root 3 all over 3. And then my left side is equal to my right side. And I can say that this has been verified. If we proved it first, you wouldn't have to verify it, because proving it would mean it works for everything. Yes? Why can't, well, right now this is grouped together. Okay? So I can't cancel out this 3 because this 3 is part of that larger factor. Anytime you have adding or subtracting, you can't factor it out. And if you're ever wondering why you can't cancel out the 3's, look at this. 3 plus 4 divided by 3. Is that equal to 4? No. Because you would, order of operations, you would add the tops and you say, this is equal to 7 over 3. But if I got creative and canceled it out, then I'd say, oh, it's just 4. No. Okay? Now, just for fun, there are some times where crazy things happen. Okay? Simplify. 16 over 64. Everybody knows you should just cancel out the 6's. Right? And it works. You're not supposed to be able to cancel out the 6's. But in that one example, it works. Right? How about this one? Sine of x divided by n is equal to 6. Cancel out the n's. It works. Okay? It works. Okay, no, you're not allowed to do that. But in certain situations. Perfect. I'm done. Right? Right? And if they ask to solve for x, it's 6 over SI. Perfect. You're just good. Where x equals the right answer. Okay. So sometimes if we're wondering if we're allowed to do something, okay, well, not that you're not, but check it with regular numbers, right? And be careful, some regular numbers throw things off, right? Is multiplying the same as adding? Yeah, because 2 times 2 is 4 and 2 plus 2 is 4. So that means 6 times 6 is 12. No. Some situations are unique, right? Now we're going to prove this one. And in this proof, I'm going to introduce you to another strategy. Okay? In this one, draw my line to do my proof. I could change tan to sine over cos, and I could change cotangent to cos over sine. And if I got both sides to be a single fraction, it would work perfectly. So the main strategy we've learned so far for proofs is change everything to sine and cos. And after you've changed it to sine and cos, get a single fraction on both sides. And I'll tell you that 90 to 95% of all the proofs you have to do in this unit, you can do that way. But sometimes that makes it longer. Another strategy that comes up is if I look on this side and see that it's in tangent, can I make the other side only in tangent? Because if I can make both sides in the same trig function, it might be really easy to figure out. And yes, in this case, I'm going to keep my left side to be 1 minus tangent, but I'm going to change So with the proofs, there are many different ways to solve this. In fact, I will show you what this one looks like with sine and cos as well. And then I'll figure out the shortest method I can figure out and show you that one as well. So if you change it to tan, this side, can you see, is already a single fraction because I can make that whole thing over 1. The left side is as simplified as I can get it. But my right side, I have fractions inside of fractions. So the main thing I want you to be able to do is if you have fractions inside of fractions and you're dividing, get a single fraction on top. Can you see that you can do that by multiplying by tan over tan? If you forget the theta, because you're just showing little work, oh, I just want to write tan, it's an E3 error. So we always have to write the variable every single time. But that will make the top of my fraction 1 minus tan theta all over tan theta. And the bottom of my fraction is 1 over tan theta. Something I do in my proofs, especially when you have fractions over fractions over fractions, I leave a little bit of space in between one thing to the next just so that things are grouped together. I also like to make my main dividing line longer and thicker just so that I can visualize what is still part of what. Now I have a fraction divided by a fraction, so I'm going to multiply by the reciprocal. Because there's a minus sign in here, this is grouped together as one factor, and the only way you could simplify something in those green brackets is if there was something identical to the whole thing in our denominator. But these ones are identical, so they can simplify. And I'm left with 1 minus tan theta. Very nice. Excellent. Yeah, or you can make your own little symbol at the end, but something that you really enjoy doing, because once you've finished a proof, it should feel good. So do something that I like making that little box that makes me happy every single time. So you do something, little smiley face, makes you happy. Draw a picture of tan, whatever you need. Okay? Okay. So we just proved that using the strategy of if I can get both sides in the same trig function, then I can get them to be the same. I'm going to do this same proof showing you that, let's say you decided copy, paste. I'm going to do the same proof and say, let's say you decided to change things to sine and cos, which is a very good strategy. If I change tan to sine over cos, I change cotangent to cos over sine, and this cotangent to cos over sine. And then I just use my fraction skills to get a single fraction on both sides. On the left-hand side, it is not a single fraction. I'm subtracting. What do I need to subtract fractions? A common denominator. So I'll multiply my 1 by cos theta over cos theta. Then I get a common denominator, so I can subtract the tops all over cos theta. Done. Left-hand side is a single fraction. Now I'm going to do the same thing on my right-hand side. Get a single fraction. On the top, I don't have a common denominator yet. I don't have a single fraction in my numerator, so I'm going to multiply this 1 by sine theta over sine theta. Then on the top of my fraction, I will get cos theta minus sine theta all over sine theta. And on the bottom, I have cos theta over sine theta. Some of you are going to be tempted to say, there's so much work I'm doing on the top, I'm not going to write the bottom. If in any step what you write next is not equal to what's above it, you're going to lose a mark. You need to always have each step below equal to what you had above. So you can't just do partial work. Oh, I'll just do a little bit of it and then a little bit later. It always needs to be, if this is on the bottom, you have to rewrite it. Sometimes you're going to get annoyed because you might have to rewrite something 5 times. And it gets really long. But now I have a single fraction in my numerator, a single fraction in my denominator, so I can multiply by the reciprocal. Can I cancel out those signs? No. Right? Since we have a minus sign there, this gets grouped together, and nothing can cancel inside those green brackets unless it's identical on the bottom. This part of my n never showed up. There we go. But this sign and this sign can simplify. So you can simplify when you're multiplying and factors are identical. Fraction divided by fraction is the same as multiplying by a reciprocal. That's fraction rule. And then those signs are the same. So what do I have? I have cos theta minus sine theta all over cos theta. Does that match up? Yes. And I said 90 to 95% of the time, if you can get a single fraction on both sides, they will work and it will be perfect. We're going to look at the other 10%, our advanced strategies we get to a little bit later. But right now, we're just trying to develop those main strategies to begin with. Okay, so we can go left side equals right side. No. Oh, that one is really nice. Perfect.
I like his previous work.
Okay. And the last proof I'm going to show you is some. You don't have to write them all down. It does not matter which way you choose. Okay. You change both things to tan. This is sort of an advanced math strategy. Okay? So I change both things to tan. Then I'm going to take this entire fraction and multiply the top by tan and the bottom by tan. You see that I'm multiplying by 1? Anytime you multiply by 1 is allowed because you're not changing what it equals to. You're just changing what it looks like with a fraction. What happens when I multiply the top by 1? Distribute. I'm going to get 1 minus tan theta. What's going to happen on the bottom? It's going to be 1. Oh, I'm done. You snooze, you lose, right?
Yeah, no, that's what just happened.
That's what just
I see now, because it's tan over tan.
tan over tan on the bottom will be 1. And here this will be 1 minus tan. Done.
Because it's tan 1 over
Every one of these methods works for every kind of question that we're going to get for this?
No, like you,
Specific one for something.
one of the things that you're going to develop is an ability to look at a question and then say, what would be a good strategy to use in this case? Okay? And you get that through practice. So on this one, you always have, I can change to sine over cos. That's like a go-to strategy. If nothing else works, you do that. Change to sine over cos and get as a single fraction. If you learn that strategy, you can give yourself 80 to 90% on all of your identities in this unit, which is a pretty good mark. If you want that 90 to 100%, well, then we add some other strategies that are more complicated for later on. But most of your proofs are just fraction work. Can you change to sine and cos? Can you get a single fraction on both sides? That is so important. And so the skills that we see in this one of getting a single fraction on the top, single fraction on the bottom, multiplying by the reciprocal, simplifying, and you're done. All right, questions for practice, but we are going to do all three of these in here. First are 3, 5, 6, and 7 II, so you don't have to do the verify.